Welcome to a deep scientific exploration of French onion soup, where chemistry meets culinary art in the most delicious way possible. French onion soup represents one of the most sophisticated examples of culinary chemistry, showcasing caramelization, Maillard reactions, and complex phase behavior all in one dish. Let's begin by understanding what happens at the molecular level when we cook onions. Raw onions are packed with simple sugars, primarily glucose and fructose, which are the starting materials for our chemical transformations. The chemical formula for these sugars is C6H12O6, and through cooking, these transform into hundreds of complex flavor compounds. As onions cook over time, they progress through distinct color stages, from raw white to light tan, then golden, and finally deep brown, as chemical reactions proceed. Caramelization is the first major chemical process that transforms our onions. Caramelization begins when temperatures reach 110 to 180 degrees Celsius, a process that breaks down sugar molecules. During caramelization, sugar molecules break apart under heat, releasing water and forming caramel compounds with rich flavors. A single glucose molecule breaks down through intermediate stages, eventually producing over 100 different flavor compounds. They give caramelized onions their characteristic taste. You might ask, why does caramelization take so long? The answer lies in the activation energy required for these reactions. The reaction rate follows the Arrhenius equation, K equals A times e to the negative EA over RT, where EA is the activation energy. At 150 degrees Celsius, the rate constant K is approximately 0.001 per minute, explaining why we need 30 to 45 minutes of cooking. Now let's explore the Maillard reaction, which occurs simultaneously with caramelization but involves different chemistry. The Maillard reaction requires both amino acids from proteins and reducing sugars, creating even more complex flavors than caramelization alone. Amino acids react with sugars to form melanoidins, brown polymers that contribute deep, savory flavors and rich color. Sugars and amino acids come together in a complex dance, combining to form melanoidins, the brown compounds responsible for that deep, umami-rich flavor. The Maillard reaction produces specific flavor compounds. Pyrazines give nutty notes, furans add caramel sweetness, and thiazoles contribute meaty, roasted flavors. Here's where we get clever. Adding baking soda dramatically accelerates the browning process by manipulating pH. Why does adding just a pinch of baking soda speed up browning so dramatically? The answer is all about pH and reaction kinetics. Baking soda, or sodium bicarbonate, dissociates into sodium ions and bicarbonate ions, raising the pH of the cooking environment. As pH increases from acidic 5 to neutral 7 to alkaline 9, the Maillard reaction rate increases exponentially, cutting cooking time dramatically. The rate increase is approximately 10 to the power of pH 2 minus pH 1, meaning each pH unit increase speeds reactions by roughly tenfold. However, we must be careful. Too much baking soda creates bitter, soapy flavors. The key is using just 1/8 teaspoon per pound of onions. Now let's dive into the fascinating phase behavior that makes French onion soup such a complex physical system. French onion soup is not just a simple liquid. It contains multiple phases existing simultaneously: solutions, suspensions, and emulsions. The broth is a true solution. With dissolved flavor compounds, fat forms tiny emulsion droplets, and gelatin creates a network structure that traps liquid. Gelatin from the stock plays a crucial structural role in creating the soup's body and mouthfeel. Gelatin comes from collagen in bones and connective tissue, which breaks down during long simmering into soluble protein strands. Under heat and water, collagen triple helices unwind and dissolve, forming gelatin that gives the soup its luxurious texture. Gelatin molecules form an interconnected network, creating a mesh that traps water molecules and gives the broth body and viscosity. The ideal gelatin concentration is 0.5 to 2% by weight, enough to provide body without making the soup too thick or gelatinous. The melted cheese on top introduces another layer of complexity, a fat-in-water emulsion stabilized by proteins. Cheese contains casein proteins that act as emulsifiers, surrounding fat droplets and preventing them from coalescing into a greasy layer. Fat plus casein creates a stable emulsion, where millions of tiny fat droplets remain suspended in the cheese matrix. Fat globules, shown in gold, are surrounded by protective casein proteins in red, creating a stable emulsion that doesn't separate even under heat. The toasted bread introduces yet another phase, a solid foam created by trapped gas bubbles in a starch matrix. Bread is essentially a foam, with carbon dioxide bubbles trapped in a gluten-protein network during fermentation and baking. The bread structure consists of a starch matrix with air pockets throughout, creating a foam that becomes crispy when toasted and absorbs soup beautifully. Toasting the bread creates additional Maillard reactions on its surface, adding more flavor complexity and a pleasing textural contrast. Understanding heat transfer is crucial for achieving perfect caramelization without burning. Heat transfer follows the equation Q equals mc delta T, where Q is heat energy, m is mass, C is specific heat capacity, and delta T is temperature change. Onions are 89% water by weight, and water has a high specific heat capacity, meaning onions take significant energy to heat up. In the cooking pan, temperature varies from hottest at the bottom where onions contact the metal to cooler at the top, creating a gradient that affects reaction rates. As onions cook, water evaporates, concentrating sugars and dramatically affecting reaction kinetics. Water activity, denoted AW, equals the vapor pressure P over the pure water vapor pressure P0, and this affects reaction rates profoundly. Fresh onions have water activity near 0.99, almost pure water, but after cooking this drops to around 0.85 as water evaporates and sugars concentrate. Raw onions contain 89% water, shown by many blue dots, but after cooking this drops to 60% as water evaporates, concentrating sugars shown in gold. Lower water activity actually accelerates non-enzymatic browning reactions by bringing reactants closer together in a more concentrated environment. Let's visualize the complete French onion soup system as a multi-phase marvel of culinary science. The complete system shows toasted bread on top, melted cheese below that, and the broth with caramelized onions at the bottom, each with distinct phase properties. Let's quantify the chemical complexity created through these cooking processes. Scientific analysis has identified over 150 distinct volatile compounds in properly caramelized onions, each contributing to the final flavor profile. The number of key flavor compounds exceeds 150, including aldehydes, ketones, furans, pyrazines, and sulfur-containing compounds. The major compound classes include aldehydes at highest concentration, followed by pyrazines, furans, and sulfur compounds, each with distinct flavor contributions. The texture and flow properties of French onion soup depend on complex rheological behavior. Viscosity eta equals shear stress tau divided by shear rate gamma dot, describing how the soup flows under stress. French onion soup is a non-Newtonian fluid, meaning its viscosity changes with applied shear rate due to the gelatin network and suspended solids. At low shear rates, the gelatin network remains intact, giving high viscosity, but at high shear the network breaks temporarily, reducing viscosity. The thermal behavior as the soup cools affects both phase stability and sensory perception. Temperature change over time follows Newton's law of cooling. dT over dt equals negative K times T minus T ambient. The soup temperature follows an exponential decay from serving temperature around 75 degrees Celsius, cooling toward room temperature over 20 minutes. Once temperature drops below 40 degrees Celsius, gelatin molecules begin to reassociate, creating a gel structure that changes the soup's texture dramatically. Let's apply our scientific understanding to optimize the cooking process for maximum flavor development. The optimal cooking temperature is 140 to 160 degrees Celsius, hot enough for Maillard and caramelization, but cool enough to prevent burning. The optimal cooking time is 35 to 45 minutes with regular stirring, allowing complete sugar breakdown without burning. Flavor development is proportional to time times temperature times reactant concentration, explaining why slow cooking at moderate heat works best. This graph compares flavor development without soda shown in brown, with optimal soda amount in gold showing fastest development, and overcooking in tan showing flavor loss. Salt plays multiple crucial roles, beyond just flavoring, affecting water activity and phase stability. Salt lowers water activity by binding water molecules and also raises the boiling point of the broth, allowing higher cooking temperatures. Boiling point elevation equals Kb times molality, where Kb is the ebullioscopic constant and m is the solute concentration. The typical salt concentration is 1 to 1.5% by weight, providing optimal flavor enhancement without overwhelming the other flavors. The choice of cheese dramatically affects the final emulsion properties and flavor profile. Gruyere cheese contains 32% fat, which is ideal for creating a smooth, stable emulsion when melted over the hot soup. Gruyere with 32% fat, shown on left, has optimal fat droplet size and distribution, while more aged cheeses with higher fat can separate more easily. Here's a fascinating question. Do Maillard and caramelization reactions enhance each other? The answer is yes. The products of caramelization can react with amino acids, and Maillard intermediates can undergo further caramelization. The synergy factor is approximately 1.5 times what we'd expect from simply adding the two reactions, meaning they amplify each other's effects. The Maillard reaction and caramelization can indeed work together in a synergistic way, producing more complex and intense flavors than either reaction alone.